Can we test the audio?
Hello, hello. 1, 2, 3, 1, 2, 3. Can people hear me in Zoom? 1, 2, 3, 1, 2, 3.
Yes, we hear it. It would be good if you could repeat the questions. In the other session, we had trouble hearing the questions.
Okay.
Hi, everybody. Thank you for attending this session. And we have 2 talks in this session. And the first one will be about highly vectorized SIKE for AVX-512. And it's a joint work by Hao, Gils, Johan, and Peter. And this will be given by Cheng Hao. And let's welcome our speaker.
Works now, right? Okay. Thanks for the introduction. Hello, everyone. I'm Hao. I will talk about our paper. This is a joint work with Georges, Johan, and Peter. So at the beginning of my talk, I'd like to mention some points. First of all, SIDH or SIKE is currently broken due to Castric decryption attack. And of course, the SIKE that we implemented in the paper and will be presented in this talk is broken version as well. And I won't talk about the security attacks and issues of SIKE in this talk, but if you are interested in the security aspects of SIKE or maybe other Isogeny-based crypto systems, I would refer you to this SIKE Broken Yet website for more information. So back to this work, the implementation and the vectorization techniques here would still be useful for ECC and other Isogeny-based crypto schemes. Okay, then let's formally start. We first look at SIDH, the short for Supersingular Isogeny Diffie-Hellman key exchange. So Alice and Bob will first randomly generate a secret scalar, and this is their private key. And with public torsion points, they will compute the secret kernel. And then they compute isogeny with public base curve, and they will get the new curve, EA and EB. So the public key includes this new curve and image of torsion point from the other side and this new curve. And then they exchange the public keys. So after receiving the public key from the other side, they use their secret scalar and compute a new kernel, A prime and B prime. And then they use the curve from the other side and this new kernel to compute isogeny phi A prime and phi B prime. They will get result curves. So the result curves on both sides have the same J invariant, and the shared secret is this J invariant. So in SIDH, there's large isogeny computation. For Alice, she computes isogenies of degree 2 to NA, and this can be done by composing NA isogenies of degree 2. And normally, a more efficient way is using by composing NA divided by 2 isogenies of degree 4. And for Bob, he computes isogenies of degree 3 to NB, and by composing NB isogenies of degree 3. Okay, so SIKE is short for Supersingular Isogeny key encapsulation. It is derived from SIDH with Fujisaki-Okamoto transformation, and the security is built on SIDH problem. So now it's broken. You can solve it in polynomial time. And SIKE comes with 2 main features: the short key length, and at the same time, the high computing cost. So there are 2 variants in SIKE. One is uncompressed SIKE, so normally you just call it SIKE. The other one is compressed SIKE, which has a key and a ciphertext compression to make the key length further smaller. So in this work, we target uncompressed SIKE. So we designed and developed a highly vectorized and optimized software library for SIKE named AVX-SIKE. So it is implemented with the latest generation of Intel AVX extension, which is Intel AVX-512, and particularly this IFMA sub-extension. So there are 2 different types of implementation in our library. One is low latency implementation, every time executing a single instance. And the other one is high throughput, or you can call it the batched implementation. So every time executing 8 different instances in parallel. And our library supports 4 parameter sets. And in the source code, there's no secret dependent conditional statements or the memory accesses. And our source code has a fixed operation or instruction sequence, which means the software is constant time. And source code is publicly available at our GitLab repository. And because the batched implementation is relatively straightforward and easy to implement, so in this talk, we focus on this low latency version. From an implementation viewpoint, SIKE has a structure of pyramid with rich arithmetic and multiple layers. So in this work, we did store analysis and vectorization for SIKE from the bottom to the top layer by layer. The bottom layer is hardware instructions. So in this work, it refers to AVX-512. And the next layer is prime field arithmetic. And on its top is quadratic extension field arithmetic, the FP square. And the fourth layer is Montgomery curve arithmetic. So it includes some point operations like 3-point ladder, point doubling, and point tripling, and some small isogeny computations like 403 isogeny generation and evaluation. The next layer is large isogeny computation. And some works have studied the optimal strategies to further accelerate this layer. The higher layers are PKE and CAM. Okay, then we have a look from the bottom. The bottom layer is AVX-512. So AVX-512 works in SIMD pattern. So SIMD means single instruction, multiple data. So as indicated by the name, it has 512-bit vectors, and each vector can be divided into 64-bit element times 8 lines. And among the sub-extensions of the AVX-512, this IFMA is very attractive for the public key crypto systems whose underlying arithmetic is large integer arithmetic. So an integer fields multiply add instruction first, multiply the packed 52-bit integers from two registers A and B, and will get 104-bit packed intermediate product T. Then it take either the lower or the higher half of the intermediate product and add it with a 64-bit packed integer from the other register C, and will store the result in the destination register R. It is supported in the most recent Intel processors like Cannon Lake, Ice Lake, Tiger Lake, and Rocket Lake. So in this work, we use Ice Lake core processor. And we only use IFMA instructions to perform the multiplication operation in our software. So which means the vector multiplier is 52-bit. And 1-bit heteronym is more friendly for Karatsuba multiplication. So that's why we use 51-bit per limb representation in the software. Okay, the next layer is prime field arithmetic. So here we use multiplication as an example because multiplication is most performance critical and the most complicated at this layer. We first define a y times z way vectorization, which means you use YFP operations in parallel, and each of them use z lines. The first implementation is 8 times 1 way. So this is easy to implement. So basically you just use AVX-512 instructions instead of x64 to batch the instances. And here the Karatsuba is more efficient. And this structure set is the example for the SIKE P503. So the 8 times 1 way implementation works on this limb vector set. And for SIKE P503, you have 10 limbs. So you have 10 vectors in this set. And there are 8 lines, so you have 8 field elements. So the next implementation is 4 times 2A. So here, for this implementation, the schoolbook is more efficient. So you have 5 vectors in this limb vector set and 4 field elements in total. And of course, you can continue to implement 2 times 4 or 1 times 8 way, but they are less efficient because there's a strong dependency in this implementation. And thanks to the rich arithmetic of SIKE, you can continue to vectorize the higher layers. Therefore, you can avoid using these less efficient variants in SIKE. Okay, we then look at the next layer, the FP square. We still use multiplication as an example. So the okay, just here. I had some text on my slides. This can you just remove it? Okay, next. So the straightforward way is schoolbook. Use the schoolbook to compute this FP square multiplication, and of course you can use a more advanced Karatsuba to compute it. So on this slide, let's forget the thing of AVX-512. We only consider the vectorization between the FP square multiplication and FP operations to see if we can parallelize some FP operations. Thank you. The easiest implementation is one-way parallelization. So basically, there's no parallelization at all. You perform the operations sequentially, and of course, Karatsuba makes more sense here. The second variant is two-way parallelization. And obviously, schoolbook is more efficient because in Kartsuba, you have only 3 multiplications, but more additions and subtractions. Since there are 4 multiplications in the schoolbook, it's also possible to parallelize them in a more aggressive way. So you have this 4-way variance. So in this layer, in this FP square multiplication, you have 3 different variants. Okay, now let's take AVX-512 into account. We should define this times X times Y times Z vectorization. And here are our vectorized implementation candidates. And the ticked implementations are more efficient. And it should be noted that for this 4 times 2 times 1 way implementation and 4 times 1 times 2 way implementation. So they both execute 4 instances in parallel. And both of them use Kartsuba for 1 layer and a schoolbook for the other layer. But according to our experiments, this 4 times 2 times 1 way is more efficient. So which means the vectorization for the lower layer has more impact than the vectorization at higher layer. Okay, now we enter the 4th layer, the curve layer. The first operation is 3-point ladder. So recall that Alice and Bob need to compute the kernel point, and the 3-point ladder is a standard way to compute the kernel. It is based on the Montgomery ladder step, which essentially consists of point doubling and differential point addition. There are already some papers about vectorizing Montgomery ladder step and the curve, especially on curve 25519 in either 2-way or 4-way. And according to their experimental results, the 4-way variant is always more efficient than 2-way for the AVX-512. So we choose the 4-way method of Hisao et al. Because in their method, there's no special multiplication with a curve coefficient, which is more friendly for SIKE. And at this layer, we should define something like W times X times Y times Z vectorization. And for this 3-point ladder, it's 1 times 4 times 2 times 1, because every time you execute a single instance and you internally vectorize it in 4-way. So for the other operations at this layer, it's possible to vectorize them, to vectorize all of them in 2-way. And we came up with a modification for the point tripling and the 3 isogeny generation. So in detail, we use C24 instead of A24 minus. So both of them are the projective curve coefficients, and you use different curve coefficients, you get the different formulas. So for the point, so here the formulas are different from the one used in the SIKE specification. So basically, this modification doesn't improve the point tripling. It has the same cost as before, but instead, for the 3 isogeny evaluation, you can save 2 2-way additions here, so that is more efficient. So for the other operations like point doubling, 4 isogeny generation, isogeny evaluations, we just vectorize the same 1-way implementation in the SIKE specification. So here are their 2-way implementations. We just have a very quick view. Okay, so to summarize the implementation at this layer, for the most of the operations, you just need 1-way implementation because every time you execute a single instance. But for the isogeny evaluation, you need implementation for multiple instances because in SIKE, it's possible that you perform different isogeny evaluations in parallel. And we have 3 more implementations in red. So they will be used in the optimized encryption operation because in that optimized encryption, it's even possible that you perform 2 3-point ladder in parallel. Okay, so the next layer is this large isogeny computation. We use 2-to-n isogeny as an example. This is algorithmic description of this large isogeny computation. So the operations in blue are our vectorized implementation to perform single instance. And there's operation in red. So this is a parallel isogeny evaluation. And according to the number of the points in the queue, you will use different vectorized implementation for that. Okay, even at the higher layers, it's still possible that you parallelize some implementation. The top is original encryption in SIKE specification. So here you have 2 kernel computation in blue and 2 isogeny computation in red. And fortunately, there's no dependency between them. So which means that you can perform two kernel computation in parallel and two isogeny computation in parallel, as we showed on the bottom. This is our optimized encryption. So after developing our software, we benchmarked it with assembly implementation of SIKE in the Microsoft SIDH library. So according to this table, our low latency implementations 2.5 times faster compared to SIDH library for the key generation and decapsulation. And the encapsulation is even 3.2 times faster thanks to this optimized encryption. And the high throughput version has more than 4.5 times higher throughput. This is a result for other parameter sets, and they have the similar speed up and the throughput improvement. Okay, so to summarize this work, the vector engines like AVX-512 offers great potential to optimize large integer arithmetic and isogeny-based crypto. And we did thorough analysis for the SIKE arithmetic in this work. And especially in the vectorized implementation, if there's less dependency, then you can get much better performance. Okay, that's it. Thanks for your attention.
Anybody has any questions? Please.
Thank you. Is it working?
Yeah, I can hear
Thank
you.
you for the talk. So I have two quick questions. First is, when you say parallelization at the higher level, I mean, does it mean more cores or just vectorization in one core? At the lower level?
Yeah, we work on the single core and the single thread.
Okay,
Yeah.
That's surprising. Did you try to change the isogeny strategies to further optimize?
No, we didn't. Actually, this can be served as the future work.
Okay.
So basically, you can run the script to evaluate the better optimal strategy for the vectorized implementation. Yeah, I understand this can improve this work, but we didn't do it in this paper. Yeah.
Thank you.
Any other questions? I mean, like, I guess I have a question, which is how much of these computational accelerations are applicable to something like SIDH?
Good question. So actually, we had a paper in last year, CHESS, that is about using the AVX-512 to accelerate SIDH. And in that paper, for the SIDH, you get the less improvement compared to SIKE because there's a stronger dependency in SIDH because the kernel sometimes is point at infinity. So this affect the software. So I guess the improvement for the low latency would be less than 2 times faster. It's around 1.5 or 1.8. I can't remember it clearly. But it's on CHESS 2021. You can check the paper.
Right, but I mean, like, surely you had more advances since, I mean, you didn't have more like computational advances since that paper, or it's just mostly the same techniques used here?
Well, compared with SIDH, so SIKE is working on the quadratic extension field. So this is a big advantage in SIKE. So which means you can do the more vectorization in that layer, as we showed in this paper. But in SIDH, it directly works on the prime field arithmetic. So you lose this benefit. And the other factor is, as I explained before, the SIDH kernel sometimes point at infinity. So at that paper, we use some hybrid method to avoid this. But if you use hybrid method, you basically use AVX-512 implementation with the x64. So this is another part that will decrease in efficiency.
I guess there's no more questions. Let's thank the speaker again.
Thank you.
And here we have the second talk of this session, basically about SIKE side channels, and it will be given by Elisa Tasso, and which is a joint work with many other people. And let's welcome Elise.
So I'm a PhD student at the in the Secure Architectures and System team at the Center of Microelectronics in Provence, in the south of France. And it's a joint research team between CEA and École des Mines de Saint-Étienne. And today I will present the paper SIKE channels, which is about zero-value side channel attacks on SIKE. And it's joint work with Luca De Feo, Nadia Elmrabet, Emeric Genet, Novak Kaluderovic, Natacha Lenard-de-Gertechin, and Simon Pontier. So first, I'm going to start with a context. So SIKE was one of the NIST round 4 alternate candidates for encryption and key encapsulation, and it's the only one based on isogenies between elliptic curves. It's relatively slow, but it has the smallest public key size, which can be very useful for certain applications. And since July 2022, there is an efficient cryptanalysis in polynomial time, meaning it's broken. However, our work can be useful to study the hardware security of other isogeny-based crypto systems. For instance, there is a paper called Patient 0 and Patient 6 by Campos et al., which applies one of the technique in our paper to C-side. Also, another interesting question is the portability of our attacks on variants of SIDH with masked degree by Morita or masked torsion point images by Furza. So let's go in and look at the building block of SIKE, which is the supersingular isogeny Diffie-Hellman key exchange. So here, Alice and Bob want to share a secret. They have at their disposal public data, so an elliptic curve and points on this curve. And each of them has a secret key, which is a scalar. The first step is the public key generation, which is a secret isogeny computation. So an isogeny is a map between two elliptic curves. Here, the starting curve is E0, and the target curve is defined by the kernel generator of the isogeny, which is P plus SKA times Q2. So it's a point on the starting curve. Alice will also evaluate this isogeny in 3 points, P3, Q3, and R3. And her public key will be finally the triplet of image points here. Bob does the same, and they exchange their public keys. The next step is the computation of the shared secret itself. So it's very similar. It's a secret isogeny computation, but this time the starting curve is defined by the public key of Alice's partner. And the kernel generator is computed using, again, the secret key and the public key of Bob. And the J invariant of the target curve will be the shared secret. So this is not enough to build SIKE. You need to add a Fujisaki-Okamoto transformation to make it in CCA. So now, what about hardware attacks on SIKE? So a very good point of SIKE is its regularity. And there are attacks that take advantage of elliptic curve cryptography in SIKE. So what you saw, the P plus SK times Q, and later of isogeny computation. There are fault attacks and side channel analysis that can be theoretical, simulated, or verified in a lab. You can see our work here in purple, that's De Feo et al. And I will also mention a work by Wang et al. That is related, called Hertzbleed. So we decided to focus on side channel analysis. Kopperman et al., Zhang et al., and Genet et al. Already performed classical DPA and CPA on the elliptic curve part of SIKE. And they all recommended the classical masking countermeasure that uses randomization, meaning you want the common characteristic between all new power traces, that is the secret, to disappear, using randomness. So here for SIKE, the points are represented by projective coordinates x and z. And we are going to multiply them with a random scalar, lambda, to get coordinates lambda x, lambda z. For lambda, you have a lot of options, p squared minus 1, p being a big prime. And this doesn't change the coordinates at all. With the projective coordinates, you still have the same quotient, x divided by z. So a bit more precisely in SIKE, you have points p with coordinates xp1, and multiplied, you get lambda x and lambda. But obviously, we want to bypass this very cheap and common countermeasure. An observation is that there is no influence of the randomization on 0. So if one of the coordinates of your point is 0, you can multiply by lambda as much as you want. It will still be 0. And this is something that we can detect with a side channel. So an idea by Goubin is to force computation of 0 value points. In our case, that would be O with coordinates 1, 0, and T with coordinates 0, 1. Kozel et al. Already proposed 0-point attacks like this on SIDH, but they cannot be ported to SIKE. And of course, we want attacks on SIKE. So the first question was, is there a theoretical side channel attack on SIKE that biases coordinate randomization? And is this attack exploitable in practice? Spoiler, yes. So in our case, with electromagnetic emissions or power consumption, and also yes, in the case of the work by Wang et al., that is Hertzbleed, where they perform a remote timing attack. And afterwards, you'd like countermeasures, obviously. So I will describe now one of the 2 attacks we worked on. So our goal is to recover the secret key bit by bit. Here, you have a diagram of a shared secret computation that you saw in the SIDH before. So you have a triplet of points. You randomize the coordinate, that is the countermeasure that we want to bypass. You have the kernel generator computation, where you get that elliptic curve cryptography part, the isogeny computation, and the J-man computation. We assume that the bits of index 0 to k-1 are known, and we are going to choose to create a point triplet such that 0 values appear in the computation if the bit we are looking for is 1, but is 0, sorry, and arbitrary values appear if the bit we are looking for is 1. We identified 2 spots in the decapsulation, so in the shared secret computation, if you want, here, that yield zeros, the kernel generator computation, so the Montgomery ladder, elliptic curve computation, and later, the isogeny computation. So we have 2 attacks. They are a bit different though. So the appearance of the first 0 value point for the 3-point ladder attack is due to an incomplete addition formula, whereas for the isogeny attack is due to the fact that we evaluate the isogeny on its kernel. In both cases, we can observe the point 0, 0 and an avalanche effect with lots of zeros appearing. We decided to validate the first attack with electromagnetic emissions and the second one with power consumption. As for countermeasures, for the 3-point ladder attack, scalar randomization is an option, but it doesn't work at all for an isogeny attack. Hence, we wanted to design an efficient countermeasure that works for both. Now, what about Hertzbleed? So Wang et al. Rediscovered independently the 3-point ladder attack, but they performed it using a remote timing side channel. It makes the 3-point ladder attack stronger, and they don't present, though, an isogeny attack. So now I'm only going to describe the 3-point ladder attack because the isogeny attack has a more complex math background, and it would take too much time. So the 3-point ladder is a method to compute P plus Sk times Q on an elliptic curve. P and Q are points, Sk a scalar. Here you can see a little toy ladder to compute P plus 50Q. You have the bits here, least significant to most significant bit. And at the start, you have 3 registers with each an input point. You can see that the contents of R0 is always doubled. It doesn't depend on the bit value. However, what happens with the other registers depends on the bit value. If you have a 0 value bit here, you add what is in R0 and R2 and store it in R2. You don't touch R. If a bit is 1, you add, what is in R0 and R. So store it in R and don't touch R2. And you just perform these little steps until you get your P plus 50Q. So now how do we perform the attack? Let us assume we want to find bit 3, which is 0. That means that we want to make a point T, which has a coordinate that is 0, appear here when the bit is 0. So we want an input point P such that here the 14Q minus P is equal to T, and there is a 0 appearing. So let's do that. So we plug such a P, compute happily as before, and indeed we have a point T when the bit 3 is 0. So if we make the correct hypothesis on the bit, T appears when bit 3 is processed. Now what happens when we make the wrong hypothesis and bit 3 was not 0, but is 1? You can see that we just have arbitrary values. This means that we can distinguish using our technique bits that are 0 and bits that are 1. So now what do we do in lab to validate it? So we attack a software implementation of the round 3 version of a SIKE 3-point ladder, and we add the projective coordinate countermeasure because it's not by default in the NIST submission, because NIST doesn't really require side channel countermeasures besides for timing. And we choose to attack an STM32F4 with a Cortex M4 at 168 megahertz, the classic NIST recommended target. Here you can see our lab setup. We have a control computer, a motorized XYZ stage, the oscilloscope, the target, and on top of the target, the electromagnetic probe to record the emissions. During the campaign, we don't move a probe, and I remind you, we want to find a bit K, knowing all previous bits. So we record multiple traces of the electromagnetic emissions of a board performing the ladder computation with 3 types of input: a random correct triplet of points, a malicious triplet such that T appears when the bit we are looking for is 0, and a malicious triplet such that T appears when the bit is 1. Here you can have a look at the traces. You can see that the trace for random inputs and the trace for the wrong hypothesis on the bits are really similar, whereas the trace for the correct hypothesis and the trace for the wrong hypothesis are really different. So to the naked eye, a human observer can guess, can find out which is the correct hypothesis. But obviously it's not very convenient to have a human observer stare at the oscilloscope during your campaign. So we decided to automate it using t-tests. So we're going to compare 2 t-tests, T0 and T1. They both use 10 traces obtained with random correct point triplets. T0, however, uses also 10 traces obtained with a point triplet that yields T when the bit is 0, we are looking for. And T1 uses 10 traces obtained with a point triplet that yields T when the bit is 1. That way, we avoid the need for a threshold on the t-test. Here are the t-test results for the wrong and the correct hypothesis, and the t-test for the correct hypothesis exhibits such high values, it's very easy to distinguish them, so we can find the value of bit k. Knowing the bits 0 to k, we can find bit k plus 1, and so on, and continue our attack. What about the countermeasure now? So the both attacks, the one about the 3-point ladder I explained, and the one about the isogeny that I did not explain, use malformed input points, meaning they don't have all good mathematical properties that are in the SIKE specifications. So they have order 2 times 3 at the power n for the 3-point ladder attack, and 2 at the power n for the isogeny computation attack, instead of 3 at the power E3 being a SIKE parameter for legitimate inputs. So we perform checks. We check that P and Q are both of order 3 at the power E3. and that will generate the Pauli-free torsion. This is done by verifying a few equations, and it protects SIKE against both attacks. How do we insert the countermeasure? Just after receiving the point triplet. If a point check is okay, we just continue the computation until we get the J invariant, else we abort. This countermeasure has a 12.9 overhead on a Cortex M4, and it has been integrated in 2 implementations of SIKE, the official submission one, PQ Crypto SIDH from Microsoft, and the circular one by Cloudflare. Now, I must say that the countermeasure has been integrated thanks to Heartbleed, because it's a timing attack, and NIST requires submissions protected against timing attacks. So as a conclusion, both 0-point attack, the 3-point ladder one, and the Isogeny one enable a bit-by-bit recovery of a secret key. We verified them both experimentally using electromagnetic emissions or power consumption on a Cortex M4 core, and the point check is sufficient to thwart both attacks. Thank you for your attention.
And we have time for some questions. Okay, so my question is the following. You mentioned that this is also applicable to some of the C-side implementations. And how well does the C-side, I mean, if you apply this to C-side, does it work equally as well as here, or?
Yeah, it works very well. Actually, the team that did that, they just checked it by a simulation, but it's a bit different than ours because we make the 0 values appear in point coordinates and then make the 0 value appears on elliptic curve coordinates, because elliptic curve coefficients in SIDH or SIKE are represented by 2 coefficients, like similarly to what you saw for the projective points. And then one of the 2 values is 0, they can detect it. And it's also a chosen ciphertext attack. They craft their ciphertext such that basically the little isogenies go back to the starting curve that has a 0 in its coefficient.
I see. I guess there's another question, which is, I mean, of course, there are many Cortex M4 platforms. And I noticed, like when some of my students were experimenting, that like low-powered versions of the M4 makes the text a lot harder. Like, did you try different platforms or just use this one?
We just used Cortex M4 because it's the standard one.
Just the discovery board. Oh no, the one that comes with Chip Whisperer, or?
No, it's I think I wrote the reference.
Okay, so the discovery board.
It's STM32F4. It's not the one on the Chip Whisperer, I think. It's a normal STM32 that you can buy.
Okay, thank you. Let's thank the speaker again. Coffee break time back at the Theater des Sommer, and see you next session. Thank you very much.